Today we will be solving problem 13 and 14 from the AMC 10A of 2021. Each of 6 balls is randomly and independently painted black or white with equal probability. What is the probability that every ball is different in color for more than half of the other 5 balls? So the problem statement is that we have 6 balls. 2, 3, 4, 5, 6 balls. Okay. Now, there's only 2 cases where they can be painted, either black or white. 2 cases. 2, and 2. Well, when we multiply all these together, we get the total number of cases, which is equal to 64. So there are 64 ways they can be painted. Okay, we want the probability that every ball is different in color for more than half of the other 5 balls. So it's saying, well, the part that gets to me is more than half. More than half. 5 divided by 2, well, for me, I just round up because it's more than half. The least possible, this is like, well, it's not like this, but what comes to my mind when it happens, more than half of the other 5 balls, more than half, the least value that's more than half is 3. So, like, let's say this ball was black. Then, like, if we chose this ball, at least 3 of the other balls would have to be white. Now, we can continue this process until we're at a stalemate with an amount of white and black balls. But this makes sense. If we choose this white one, there's 3 more, white, 3 more. So this is sort of like a pattern, 3 blacks and 3 whites. So now we want to find the number of cases where this is possible. We were given that, well, there's 6 balls here. 6 balls, you choose 3 out of it. This doesn't matter because, well, this is 3, choose 3, that's equal to 1. Now, when we solve for this, we get 6 factorial divided by 3 factorial times 3 factorial. From here, we get 20. 20 ways this is possible. Now, we 20 divided the ways, like the amount of successes divided by the total number of cases, which is 64. Will this will give us our answer, which is 5 over 16. So this is the probability of having of painting the balls like this. Now we're gonna solve problem 14. How many ordered pairs of x and y of real numbers satisfy the following system of equations? X squared, this is plus 3y equals 9. The absolute value of x plus the absolute value of y minus 4 squared equals 1. Okay, so what we're going to do here, our strategy, is to graph these. Let's take the first one. This is fairly simple to graph. From this, we get that x squared. Well, we can just find the intercepts of this. When y is equal to 0, x is equal to positive or negative 3, and then when x is equal to 0, y is equal to 3. Okay, sounds simple enough, right? Yeah, that's correct. So, this is our y equals 3 point, and our x equals negative 3, and our x equals positive 3. This is a parabola because it's a quadratic. So what we can do here is we can draw this parabola. That will look something like that. Yeah, that's kind of how it's work. Alright, so we can do the same process with this second equation. This is a bit harder to do, but it is still possible. What we do here is we actually take the square root of both sides. From this, we get the square root, absolute value of x plus absolute value of y minus 4 equals positive or negative 1, meaning that absolute value of x plus the absolute value of y, this is equal to, well, there's two values, 5 or 3, depending on how you look at it. Now, these absolute values are kind of vague. We don't know if x is negative or x is positive, or if y is negative or if y is positive. But we can graph these in a sort of like diamond shape for all the things we don't know. Let's start with 3. Yeah, let's start with 3. X plus y is 3. Well, when the absolute value of x plus the absolute value of y equals 3, both of them, the absolute value of x equals 3 and the absolute value of y equals 3, because those are the intercepts. Now we can, well, it could be positive or negative, but we don't know. That's why we have to graph it in a diamond shape for all the values that we don't know. Well, look, it already collides with the parabola, but now it's like a rectangle with a negative 3, so you have to connect it like this. We can do the same thing with 5. Both the intercepts are 5, but again, we don't know if it's positive or negative. So we have to resort to this diamond-looking shape. Now we have this peculiar drawing. Now, basically what we want to find is how many ordered pairs of real numbers satisfy both of these equations. Well, what we did here, we drew this to prove how many, well, let's see here. So, we have this drawing with the parabola and the two diamonds, one small and one's big. What we want to find is how many ordered pairs of x and y fit these constraints. Basically what we're talking about, in other words, in simpler words, how many times does the two equations meet? There's one here, one here, one here, one here, and one here. There's 5 points in total, so our answer is going to be 5.